oil is mainly used for transportation. And this enormous number here, 90 million barrels a day, you know the barrel price. If you multiply this now with the barrel price of 160 or 80 dollars per barrel, you see how much money is being made out of this oil. But I would like to turn this to another number, and this is this 2 liters a person. So if we convert this down and divide it by the population, we see in average, every person worldwide consumes per day 2 liters of crude oil. The number changes. If you go to Germany, this will be 4 liters per person. Just think how much crude oil this is if you consume 2 liters of crude oil per person per day. So should we be worried that we will run out of oil? And the answer is no. We have here the ratio of reserves to production, and you see the gray one is the worldwide number, and you see this worldwide number is stable around 50. Doesn't change much. Here in the beginning of the 90s, I started studying chemistry, and since I started studying chemistry, this number is going almost flat until now. The reason for that is that on one hand, we are getting much more technology to exploit new fields, and this is, for instance, here in South America, in Argentina, they suddenly found some offshore oil, and you see now this number gets up strongly. You see that Middle East, this is what the people are worried that this number is going down, but in all other countries it's going flat. So on the one hand, because of technology, we can exploit the fields in different locations, we can find new fields. On the other hand, there's technology to extract more oil out of the ground. This is called enhanced oil recovery technology, and you can essentially extract more and more oil out of the oil wells, and therefore also this number stays constant. So there's no worry about that we will run out of oil within the next 60 or 80 years or so on. So peak oil so far, this is the idea, the peak oil, after this peak it starts going down. Some people predicted, but the numbers never showed any indication that we're gonna see a peak oil. So what's the problem? The problem obviously is the carbon dioxide. So when we look at the carbon dioxide worldwide, we see that the carbon dioxide emissions are going up strongly. This is the last 30 years. In some countries, it went up 300% in developing countries. In some countries, it stays at a very high, level, and it does not really decrease. See that China bypassed the US in the last 20 years. You see that in some countries it's going stable, and sometimes it even goes down slightly. This is because of more efficient technologies, but essentially the carbon dioxide emissions are still high, and there is no sign that these carbon dioxide emissions will go down. And we all know, and most of the people nowadays trust the scientists, that these carbon dioxide emissions will increase the temperature on the Earth, and this will not be a very good, will not end up in a very good situation. In average, to give you also a number, I like very much to give you numbers which you can relate this to, because million tons a year in China is very difficult to relate to something. In average, we have currently a carbon dioxide footprint of 7 to 8 tons per person per year. If you relate this to a flight to Singapore, if you buy a ticket, so nowadays in Europe, they print always the carbon dioxide cost onto such a ticket. One flight forth and back to Singapore is from Germany is about 2.5 tons CO2. So if you fly 3 times to Singapore, you exceed already the average carbon dioxide footprint of a single person. So that's not good. Where does the carbon dioxide come from? And we see that carbon dioxide comes from energy and heat. Electricity board, I just mentioned, transport produces a lot of carbon dioxide. We see carbon dioxide produced in industry, that's ammonia production, steel production. We see carbon dioxide produced from the building industry, so this is essentially producing concrete. And there are some others. We see obviously this in transport would call for biofuels. So biofuels, how do the biofuels look like? And I showed you already, biofuels are increasing strongly. And we have in here the biofuel production, consumption. What is the consumption? And we see obviously we have a lot of biofuel consumption. And in the US, North America, pretty big. There's flat spots. I don't know if this is related to the last 4 years, but it is somehow. And you see that the biofuels are going up. And this is this most strongly increasing field in the energy sector. I showed you most others are running more or less parallel. The biofuels really went up over the last 20 years or 10, 20 years or so. Still, you see that the amount of biofuels, although this number is going up strongly, it is maybe here 2 to 3% of the oil production. So it's a small part, but still increasing, and it will get very important in the future. When we could look at what biofuels are, we see that biofuels is usually largely biodiesel. In the US, in Brazil, it's also ethanol. And this brings us to the point how you are producing biodiesel and biofuel. And when you compare now the bio and fuel production pathways, and I didn't have time much today to talk about the current state of the art. This is what from fossil fuels, when you make fuels, essentially you get the crude oil, you go to a refinery. I told you there are about 400 refineries in the world. What you do in a refinery is essentially redistribute the carbon chain length. So crude oil has a very long carbon chain, has very contained substances, very long chains. You cannot put this into a car, so you have to cut it short. This is what the FCC, the cracking process, does. So you refine it, you cut it essentially short, so you redistribute the chain length of the carbon inside the molecules. You cut them essentially. You also remove sulfur. You always increase gas, the octane number, and you end up what this is an English slide. We end up with petrol. So this is the English word for gasoline, and you get diesel. You can get also fuels out of natural gas. This is essentially you can either use it directly or you convert it to synthesis gas. Synthesis gas is a mixture of carbon monoxide and hydrogen. We're going to look at this in a moment. And from the synthesis gas, you can do Fischer-Tropsch and you make liquid fuels. And you can also make ethers out of the synthesis gas. You can make methanol and so on. So there's ways from natural gas. There's ways from coal. So this was initially what Fischer-Tropsch was developed for. You start with coal and you gasify the coal. You go towards synthesis gas and you make gasoline. For biomass, you have different ways. And biomass, essentially, we discussing different sources of biomass. So that's the first generation biofuel. First generation biofuel, here in red, like sugar and oil, is competing directly with the food chain. This is what's currently done. You can convert these biofuels directly to biodiesel or via fermentation towards ethanol. This is under discussion because it directly competes with the food chain. There's second generation biomass here in blue. This is essentially industrial waste from production, either special plants or waste from producing plants. So it doesn't compete directly with the food chain, but it competes with the space required for growing plants. So you can either grow on a field some food, some whatever wheat, or you can grow special plants for oil production. This is what they call second generation biofuel. So it doesn't compete with the food chain, but it competes with the space, with the field space. And there's a third generation. This is essentially where everybody goes to currently or discusses. This is when you make fuel out of waste. And I will show you some examples how you can use this waste. And obviously this does not compete. There's a lot of biological waste and you would like to convert to waste. What are the processes in biomass conversion? Essentially, you see that biomass contains a lot of oxygen. And this oxygen, obviously, in the gasoline, you don't like to have such a high oxygen level. So you have to remove the oxygen. And the oxygen can be either removed by decarboxylation, so carbon, you decarboxylate it and you remove the carbon dioxide. This can be done, not easy in many cases, but it can be done. It's a catalytic process at high temperature. You can, on the other hand, can hydrodeoxynate it. So you remove the oxygen here with hydrogen towards water. So this obviously doesn't produce carbon dioxide, but it needs a large amount of hydrogen. If you do this reaction, then you can get, again, an alkane, and you remove the oxygen here as water. So this brings us to the discussion how you're making the hydrogen. And this is the normal way of producing hydrogen. I told you now hydrogen is produced, when I mentioned already for ammonia synthesis, hydrogen is produced out of natural gas. So you're feeding the natural gas, you correct natural gas together, so methane essentially with water towards hydrogen and carbon monoxide. This is what I told you, this is so-called synthesis gas. For the synthesis gas, you can either produce liquid fuels by Fischer-Tropsch, you can use methanol and so on. So that's quite a standard production. This is standard production, how you produce all the methanol worldwide. You can then convert this carbon monoxide and other reaction conditions and other catalyst with water towards hydrogen. So you see you get hydrogen and carbon dioxide. So this is the way how to produce hydrogen nowadays. And this hydrogen then might go toward any hydrogenation. This hydrogen goes into ammonia synthesis. So you see ammonia synthesis also, you're not seeing any carbon dioxide in the ammonia, any carbon involved in the carbon in the ammonia. Produces a lot of carbon dioxide because it's essentially, this is the way how you produce the hydrogen. You can do something about that, and this is done already sometimes. So this is what sometimes is nice. You can capture the carbon dioxide. If you capture the carbon dioxide, you can remove it. This is essentially a process shown here. You have a 2 or more bedded Stover system. It's an amine-based system. You take out the carbon dioxide because the exhaust gas, if you have here in industry or power generation or whatever, contains obviously a mixture of nitrogen and carbon dioxide. You have to remove the carbon dioxide by absorbing it, and then you can either store it, and then if you store it underneath, it's called CSS, carbon capture and storage, or you can utilize it at the CCU. You can utilize it to make, you can directly use it here. EOR stands for enhanced oil recovery, so you can pump it down to get more oil out. You can use it for food or solvent industry, or you can convert it towards fuels. And this is what we will discuss in a moment, just to mention it here. So this is the way what you can do with the way of hydrogen. There's another way of producing hydrogen, and this is what you call green hydrogen. So this hydrogen is called black hydrogen, and there is even pink hydrogen and yellow hydrogen. Pink hydrogen, for instance, is hydrogen produced out of electricity from nuclear power plants. So there's green hydrogen, there's black hydrogen. The green hydrogen is essentially by electricity, and you see the price is a factor of 3 times higher. So the carbon dioxide removal gives you a factor of 2. So this costs not $600, but $1,000. If you would like to do that by electricity, you come up with about a factor price of 3 times higher. You can do that, but you see the price tag is enormously higher. 3 times is nothing you can easily take. So after having said that, the price is 3 times higher, we have to consider how we're making the electricity. And if you look in Germany, for instance, here, electricity, you see in Germany, we are having roughly 1/3 renewables currently. So wind, solar, hydro, and biomass is 1/3. There's a significant fraction of nuclear electricity, which is going down currently. And we have 50% from fossil fuels. Germany, because the particular situation in Germany, because Germany has a lot of coal, not so much gas, we have a large fraction of coal. If you compare this to the US, you see the US uses less renewables, similar fraction of nuclear, has a large fraction of fossil fuels, but has a very large fraction of gas compared to coal. This is due to the enhanced methods for getting gas out of the ground. Some people call it also fracking. And that's good. Because if you produce electricity out of natural gas, you're combusting methane, so you make 2 molecules of water, 1 molecule of carbon dioxide. If you combust coal, you're making only carbon dioxide. So already using natural gas will lower the carbon dioxide footprint. And this is why, if you compare to Singapore now, Singapore does 95% natural gas. That's so bad because natural gas among the fossil fuels give you the best carbon dioxide balance of all fossil fuels because hydrogen methane contains the highest amount of hydrogen. Why this is not surprising, because essentially this requires here a lot of space. So you would like to Germany, that's the estimation that when you would like to go to wind only, that you would need 10 to 15% of the land area of Germany to have all these windmills installed. And obviously, if there's limited space like in Singapore, this is very unlikely that this is going to happen. So what can you do, and what is the main problem with renewable energy. The main problem, or the main challenge, you would like to call it, is that you have fluctuations. So sometimes in Germany, I have seen 1/3. 1/3 is enough if it's a sunny afternoon on a sunny Sunday afternoon with some wind. Everybody sits outside, enjoys life, and we have a lot of wind and sun. Then even the production is high, and even this 1/3 is sufficient in Germany to run only on the renewables. But there are also days like today, it's raining outside, it's cold, it's winter, industry takes a lot of energy, there's not much sun, there's today also not much wind in Munich, so you're down there. So you have significant fluctuations in the amount of renewable energy produced via renewable sources. And obviously now you have to find ways of storing that. And I've shown you already, storing that in batteries is not very effective. You should store this in chemical bonds. And this is a project we are working on. It's funded by the German science funds. It tries to accept these fluctuations, and via catalytic processes turns this energy, together with water and carbon dioxide, turns this energy into energy carriers. And these energy carriers can be methane. You can store it as methane. One possibility, you can store it in form of hydrocarbons. You can store it in form of alcohols. This is what we are doing. You can do liquid oxygen, liquid oxygen hydrogen carriers. These are, for instance, formates and those things. And you can also make ammonia. And ammonia is, especially in the Nordic country, heavily favored as energy carrier, because you can see now you make ammonia. If you get the electricity to get the hydrogen out of electricity, you convert it with nitrogen. You convert ammonia back to hydrogen, hydrogen and nitrogen. See, there's not even any carbon dioxide involved. So this is completely carbon dioxide free cycle. The only disadvantage is that you're storing ammonia, which might cause some risks. So you don't want to have thousands of tons of ammonia stored somewhere, but this is still a way of storing. It's discussed as a liquid, as a way of storing energy. What we are doing, and so let's have a look a little bit what we are doing in this project, is that we start here with the removal of carbon dioxide. We take the carbon dioxide. If you go to a power plant, obviously you have to separate the carbon dioxide, and I've shown you already in the separation process you use amine-based solvents. You bind the carbon dioxide towards an amine functionalized catalyst, and this amine functionalized catalyst activates the carbon dioxide in forms of a carbamate or amide on the surface. And now, after saturating all the ammonia, so with all the amines, with the doing a sorption process, you have to regenerate, and we are now utilizing. So I told you this is a concept of carbon capture and utilization. We utilize it by using hydrogen, which obviously comes down it's a green hydrogen in best case. We use it as a hydrogen in a catalyst, and we convert it directly towards methanol, and that works decently, obviously. Still, there's always a way of improving it. This is a priority program within German academia, and we have all partners here all over Germany. So what you can do with this methanol, you can use directly methanol as fuel, but you can also convert it to oxymethylene ethers. This is called OME. Somebody in Germany, people list that already. I don't know if this is already discussed worldwide, but this is a very novel e-fuel. So we start, and I've shown you already, convert the carbon dioxide with hydrogen towards methanol. And this methanol can be easily converted to dimethyl ether, but you can also insert more of these ether groups. And this is called OME, and OME essentially has a number. So OME 0 is, if this number is 0, so this is dimethyl ether, and then you have 1 up to 5. It's a catalytic process using acid catalysts, and you can get different chain lengths here for this OME product. And this OME directly can be a so-called plug-in fuel. So this fuel, if you use OME, or you blend it into gas and diesel, or you can use it directly as diesel. So you don't have to change the infrastructure for distributing the liquid. You don't have the energy carrier. You don't have to change the engines. You just only create different fuels out of, this case, using electricity out of green hydrogen and carbon dioxide, which you capture from air or you capture from a carbon dioxide source. Might be even a power plant, which then turns a power plant obviously into a carbon dioxide free, almost carbon dioxide free energy production. What's interesting here, and I don't have enough time to go into this in too much detail, is if you look at the particulate and NOx trade-off. So every diesel engine, people working with diesel engines know that you can either run a diesel engine at low NOx emission, but then you have a relatively large amount of particles, or you can go down with the particles, then you produce more NOx. And you see that this OME has a big advantage of having almost a very low particle level. And the particle level, the soot or the carbon level is essentially very low, because this gasoline here, the particular interesting thing, does not have any carbon-carbon bond. No, OME is not a GUI paste. This comes later. OME is a very nice liquid. It's not a GUI paste. As we talk about the GUI paste, very good. It gives me the transition to the next example I want to show you. If it's always the same problem I'm having. If I once go to the chat, then it doesn't go any more further. Here goes. This is the GUI paste, and the GUI paste is essentially you call this this GUI paste is biocrude. Very good comment from the chat. So essentially, this is another project, and this is also we are working on. This is an EU project. You see, together with many industrial partners and some academic partners, and this is what this GUI paste comes from. So you take waste, and we have discussed already that you're having a third generation biofuel, so something which is biofuel, which is essentially produced out of waste. In our project here, we are using remainers from a water treatment, so-called sewage sludge. And this sewage sludge is thermally cracked in a high temperature, high pressure process into this biocrude. And this biocrude now is a black mixture, not really flowing nicely, mixture, aqueous and organic phase. So you cannot directly put it into any car. And you have to work it up. And we in our project have decided to go 2 steps. So the first step is electrocatalytic. So by electrocatalytic process, we're trying now to reduce, and I will show you that it is possible to reduce the carbonyl group, to reduce the unsaturated bonds. At the same time, you're producing hydrogen. And then you go to the second step, and you do with the hydrogen produced. So this electrocatalytic conversion gives you, on one hand, reduces the chemical functionality inside this material. On the other hand, it produces a certain amount of hydrogen. And this then goes to the hydrogen treatment, and you do with a conventional catalyst, you're converting it down to biofuel. Again, this is a drop-in fuel, so again, it will be a fuel which can be used in any standard diesel engines. We are doing this part here. Our partner is doing this part here. And I also want to show you some scientific detail, because it was interesting to see what we are doing out of this very complex problem. And we are using here electricity for reducing chemical molecules. And we start here with a model compound. I usually use model compounds, not directly in first step, we're just in the first step of this process, not directly the biocrude. And we're using here paraglycerol to reduce it down to the alcohol. And you see that essentially you can do this by, if you have an electrocatalytic process, you can do this by generating the hydrogen via electrocatalytic process. So the hydrogen is on the surface of the catalyst, the cresol is inside the liquid phase, and we're going to reduce that down with this. You see, first we have here the hexanone, and we're again going from the hexanone towards the alcohol. So you use this on the surface of the catalyst. You can do the same thing with putting in hydrogen in the gas phase. Don't have any electricity. You have a catalyst in, the hydrogen will go into the liquid phase, standard hydrogenation chemistry. The hydrogen solves inside the liquid phase, it goes to the catalyst surface, dissociates, and acts as a reducing agent. And you see that the activity in both cases is the same. So essentially what we're looking at is activity of hydrogen on the surface, no matter how the hydrogen is being produced. To get this, obviously, you have to align the chemical potential of the hydrogen in the gas phase with the chemical potential created by the hydrogen on the electrochemical process. Okay, it's still early in the morning. And you do this by looking at the open circuit potential. Essentially, the open circuit potential allows you to align the chemical potentials. But then if you write down the chemical potential, you see this is the chemical potential on the electrolytic process. Here we have the charge, the potential in the electric process, the Faraday constant, the electrons, and we have here the influence of the pH value, which also influences here the reactivity. This is the chemical potential in the gas phase. You see the chemical potential in the gas phase is directly proportional to the pressure in the gas phase. So essentially, no matter where it comes from, and this is, I think, a very interesting concept, no matter where the hydrogen comes from, the hydrogen might come from an external source, the hydrogen might come from electrocatalytic process. You get the same reactivity. And we're still quite happy because thermodynamics should not differentiate where the hydrogen comes from. And this is where we started also our lecture saying the process itself is always driven by thermodynamics. If the process is feasible thermodynamically, it can happen on a catalyst, it can happen every catalytic pathway. It might be a standard thermal catalytic pathway, might be electrocatalytic, might be photocatalytic, whatsoever. It's all driven by the thermodynamics. And if it's feasible thermodynamically, it might be different rates, but the reaction itself proceeds similar extent. Okay, with this, I think it's time for me to summarize my talk today. So this is a slide out of the energy translation towards carbon dioxide-free fuels in Germany. And we see, and I'm convinced we're going to see for CO2 neutral transport fuels, we see still using conventional engines, using either biofuels, and I've shown you we go towards third generation biofuels, or e-fuels. E-fuels are produced using green hydrogen, and this green hydrogen together with the carbon dioxide gives you what's called e-fuels. There's electromobility. Electromobility will have a large share, and there will be fuel cells. And when we compare that the two processes, essentially batteries and combustion engines, you see that from production of the site, you see you lose not much. So if this is the efficiency, you see you can get the oil out. The refining is very efficient. You have to move the fuel towards the tank. So you don't lose much here. Essentially, you lose most of the efficiency inside the car. Because a diesel car, most of maybe around 30%, a little bit above 30% efficiency if it's still driving, but if it's stuck in a traffic jam, the efficiency is very low. If you compare this to electrical, we've seen obviously we have to produce the electricity, and if we produce the electricity still out of fossil fuels, it's also not 100% effective. We also produce a lot of heat, so the efficiency is also about 40%. If you produce it via renewables, anyhow, this is not changing. Transport is not doesn't lose much. And you see also here the efficiency is much better of electrical car, because if the electrical car is stuck in a traffic jam, obviously doesn't consume any energy. The fuel cell car is a little bit a mixture of both, because you have to convert first, make the hydrogen, then you make the electricity, then you make the hydrogen, and then you are going towards the fuel cell car. So we see two different ways essentially, and we see both. And the advantage here is that you can store a lot of energy at a much better volume ratio in chemical bonds than you store it in form of electrons. So let's summarize this talk, and I hope that I've shown you today that we'll see diverse solutions in the future. We'll have a certain fraction of fossil fuels, and carbon dioxide removal will also get it carbon dioxide free. We will see an still increasing amount of biomass. We'll have wind and solar energy. This depends on the location you are in the world, on the space you're having. So this depends very much on the world where you are. When we look at concepts towards CO2 footprint reduction, we see that usually now the production size, the processes we are doing, they all scale with size. The Fischer-Tropsch process scales with size. The larger the process it is, the more effective it is, mainly because of the energy balancing. And that's really a huge investment cost. So Fischer-Tropsch plant, usually in Qatar, there's some in South Africa. It's a very big investment. And now, if you would like to go to an energy transition in the next 15 years, it's very unlikely that you're going to build up a plant, which then maybe goes for another 15 years, because it takes you 5 years to build that, and you would like that this plant is running for another 50 years if it's just a large one. And therefore, everybody expects that the new technology, and this is a large field of development, which, for instance, you could be involved if you study the Masterclass in chemical technology, industrial chemistry, we go towards smaller processes. So we try to get smaller processes which are cheaper, which are as effective, and will be decentralized. We will also see the individual solutions for the transport. So you cannot say transport is all cars. We know trains are running all on mostly running on electricity. Underground is running on electricity. Bicycles, scooters, there the transition is almost completely towards electricity. Currently, we see a transition in cars. We see that there's an increasing amount of cars being used with batteries. There's still a larger fraction, obviously, with normal engines. But the other ways of transport, there's the flying, the planes, very unlikely that they will fly in a plane with batteries. Even more unlikely if one day maybe you're going to see that it will fly with a rocket somewhere. It's also very unlikely that this is be done on batteries. The other ones is ships. Very unlikely that they have these container ships. If you look in Singapore out and see all these huge container ships, very unlikely that this will run on batteries because they're essentially the load. So we have to reduce the load capacity if the storage has a factor of 3 or 4 in the compared to liquid fuels, then obviously you have to reduce the payload to a factor of significantly, and this will be also very economic limitation for them. So cars is currently the field. Most things are going to change and most development will be on, but there are still other ways, and there are still ways where you really rely on, I think, for a long, long time on liquid energy carriers. And therefore, and this is why I was the topic, or main topic of my lecture today was a little bit short, but is a processes for a cyclic carbon economy. And I've shown you that there's biofuels and e-fuels. Both are carbon dioxide neutral. And with this, I would like to finish my talk and would say that energy transition is not only battery cars. There will be other ways, and chemistry will be still important and will be even more important because you have to produce new process. The last 30, 40 years, there were not many changes. The refining itself still was the same about 50 years ago. Some refineries are even 50 years old or even older. So the processes there, they got modified a little bit, but there was not really a change in the processes. Now we're going to see a change in the process. We're going to see that we need different ways, carbon dioxide-free fuels, and therefore there will be a lot of development, and there will be a lot of development in catalysis and a lot of development within the industrial chemistry. With this, thank you for your attention and happily answer all your questions.
Thank you, Prof. Yantis. So everybody, if you have any questions, you can just throw your questions at the chat box, or you can unmute yourself and then ask the question directly. All right. So the questions for the topic will be directed to Prof. Yantis. And then if let's say you want to know more about the MSc in industrial chemistry, you can just direct the question to us. Yeah, any questions?
No questions at all.
It seems like your lecture is pretty clear, so everybody enjoying the talk.
Okay, there's another explanation, but I don't want to say that. We don't have to. Do we see the students? Not what I found out from teaching. Everybody turns off his camera, so we never know what they are doing.
Sometimes.
Okay, if so, I hope that I've shown you that going to the staying within chemistry and not going always battery research. So staying really within catalytic processes is something which will be in the future always required. And if you participate or if you sign into the class of industrial chemistry, we might have the chance to see each other next spring, and I hope we do that. So next spring, next March is the it's March? No, it's September. The class is in September. Hopefully I can come again in September to Singapore. I really enjoy Singapore, and would be interesting to see you, and maybe we can discuss there. Okay, now we have a question? Okay, good. If there's nothing to discuss, I'll let you with people from Asia, and if you have any question about the class itself and about the organization and about who is teaching what and when and how, you can get together with them. Okay. Bye-bye.
Bye. Thanks, Prof. Yantis. I will get in touch with you.
Thank you and bye.
Bye-bye. So you send me an email afterwards or what?
Yes,
we can talk afterwards. I have next teleconference, I think, at 11. So we still have 1 hour time that we can discuss afterwards if something is to discuss. But
all right, cool.
not necessarily. Okay. Bye-bye.
Bye-bye. Thanks, Prof. Yantis.
Bye-bye.
So hi, Ilham Shah. I have a question from you. Do you have any personal contact to consult about the chemical industry or continue master degree? All right. So I'm here. Yeah. You can ask any question pertaining to the admission about industrial chemistry. So what do you want to know?
Okay, thank you. I will contact soon.
Sorry.
Okay, I will contact the university to ask about the information.
All right, you can email me. I'll type you the email address. Give me a moment.
Okay.
Okay, that is my email address. So everybody, in case you still have some doubt with regards to our program, you can email me and then I will answer your queries accordingly.
Okay, thank you, Ms. Lenny.
Yeah. Any other questions from the rest of the participants? Since we are still here, although Prof. Yantis already left the room because he has a conference to attend. Yeah, we are still here. If you want to know more about the program or admission requirement or any other things. All right. Since there is no response, I guess that's all for today. Yeah. Again, thank you very much for signing up and attending for this masterclass. We do hope that Prof. Yantis' lecture today really benefited everybody. So like Prof. Yantis said just now, this is just a teaser to our master degree of MSc in industrial chemistry. So if you want to know more, you can just go to our website, www.tum-asia.edu.sg, or you can email me, yeah, lenny.christina@tum-asia.edu.sg. Okay, thank you so much. I wish you a great evening. Bye-bye. Bye-bye.
Bye-bye. Thank you so much.
Thanks.
Bye. Thank you.